Something strange is happening to Earth right now. Deep beneath your feet, the planet's solid iron core has slowed down and started spinning backward. Above your head, the magnetic shield protecting you is cracking open over the South Atlantic. Days are getting shorter. Fireballs are slamming through roofs in Texas. The Gulf Stream just jumped 136 miles north. If you find this as gripping as we do, hit subscribe and like before we go any deeper. What you're about to hear isn't theory. It's measured, recorded, and unfolding right now. Brace yourself. We begin. 3,000 miles below your feet, a solid ball of iron the size of the moon just changed direction. For decades, scientists believed Earth's inner core was a quiet, predictable thing, a frozen heart locked deep inside the planet, spinning faithfully along with the rest of us. That picture has been shattered. In a study published in the journal Nature, geophysicists at the University of Southern California analyzed seismic waves from nearly 200 pairs of repeating earthquakes recorded between 1991 and 2024. Their findings stunned the scientific community. Around the year 2010, Earth's inner core stopped spinning faster than the surface. Then it began drifting backward. This is confirmed, not theory, not speculation, confirmed by seismic data analyzed by multiple independent teams. Picture it, a massive iron-nickel sphere, hotter than the surface of the sun, suspended in a churning ocean of molten metal. For most of recorded scientific history, this inner core rotated slightly faster than the planet's crust. A superrotation, scientists called it. Now, for the first time in roughly 40 years, it has slowed to a crawl, fallen behind, and started moving the other way relative to where you're standing. How do we know this? Through a clever trick, geophysicists hunt for what they call doublet earthquakes. These are pairs of quakes that strike the exact same spot, years apart, producing nearly identical seismic signatures. When the seismic waves from these twin earthquakes pass through the inner core and arrive at recording stations in Alaska and Canada, scientists compare them. If the core hadn't moved, the waveforms would match perfectly. They don't. The waveforms have been shifting, drifting, telling a story no one expected to read. John Vidal, the geophysicist leading the research, described what they uncovered. The core's slowdown matches a roughly 70-year cycle. The last reversal happened in the 1970s, when nobody had the tools to detect it. This time, we caught it in the act. But here's where things get unsettling. The inner core isn't just slowing. Newer data hints that its surface might be morphing, reshaping. Some scientists believe the boundary between the solid inner core and the liquid outer core is undergoing what they call viscous deformation. The deepest part of our planet might be physically changing shape as we speak. Why does this matter to you? Because that liquid outer core surrounding the inner sphere is what generates Earth's magnetic field, the shield that deflects deadly solar radiation, the invisible bubble that lets life exist on the surface. When the engine at the center of that machine starts behaving in ways we've never seen before, the consequences ripple outward in ways scientists are only beginning to understand. Some researchers speculate this could subtly shorten or lengthen our days by milliseconds. Others worry about long-term effects on the magnetic field itself. A few quiet voices wonder if this is connected to other planetary anomalies showing up at the exact same moment. The truth is, no one fully knows. The inner core sits 3,100 miles beneath the surface, in a place no instrument can ever reach. Everything we know comes from waves passing through it, and those waves are telling us the heart of our planet has done something it hasn't done in living memory. A reversal at the core would be strange enough on its own, but it's only the beginning, because directly above that wobbling iron heart, the shield it generates is tearing open. Off the coast of Brazil, far above the rolling waves, there is a hole in the sky. You can't see it, you can't feel it, but every satellite that crosses this patch of atmosphere holds its breath. Computers crash, memories glitch. Hubble itself shuts down its sensitive instruments whenever it passes through. This region has a name: the South Atlantic Anomaly. It's a vast, weak spot in Earth's magnetic shield, a place where the protective bubble that wraps our planet thins out so dramatically that deadly cosmic radiation pours through and reaches the upper atmosphere. And right now, it's growing. Data confirmed by the European Space Agency's Swarm satellite mission paints a startling picture. Since 2014, the anomaly has expanded by an area nearly half the size of continental Europe. Half of Europe. In just over a decade. Picture France, Germany, Spain, Italy, the United Kingdom, and Poland combined. Then imagine that much new weak zone forming above the southern Atlantic Ocean, stretching from South America almost to the southern tip of Africa. The Swarm satellites have been watching this since 2013, 3 small spacecraft flying in formation, mapping every flicker and ripple in our magnetic shield. What they revealed in 2026 left geomagnetism experts shaken. Chris Finlay, professor of geomagnetism at the Technical University of Denmark, led the analysis. He told the European Space Agency something remarkable. The anomaly is changing differently in different places. Near South America, it's expanding steadily. But southwest of Africa, since around 2020, the field has been weakening at a much faster rate. Something special is happening in that region, something causing the field to collapse in ways scientists have never observed before. What does this mean in numbers you can picture? At the eastern edge of the anomaly, the field strength dropped by about 600 nanoteslas between 2018 and 2025. That's roughly 3 times faster than the weakening on the western side. A lopsided collapse, as if something deep inside Earth is yanking on the field unevenly. Astronauts feel it. International Space Station crews report seeing strange flashes of light behind their closed eyelids when they pass through this zone. These are not dreams. These are cosmic ray particles slicing through their retinas. The flashes are direct hits to their optic nerves. Satellites suffer too. Operators of the orbital telescopes, communication networks, and weather satellites all know to expect glitches when their hardware crosses this patch. Some operators temporarily shut systems down. The Hubble Space Telescope, that priceless instrument that has shown us the deepest reaches of the cosmos, simply turns off its detectors when crossing through. Otherwise, the radiation would corrupt its data. Now imagine what this means for the future. The Earth's magnetic shield is what stops the solar wind from stripping away our atmosphere. It's why Mars, with its dead core and collapsed magnetic field, became the cold, dry husk we see today. We are not Mars, not yet, but our shield has a tear in it, and the tear is widening. Is this the beginning of a full magnetic pole flip? Scientists don't agree. Some argue the anomaly is part of a normal centuries-long cycle. Others worry it might be the prelude to something far larger. Whatever the answer, the most disturbing detail isn't the size of the hole, it's what's causing it. Because deep below the anomaly, scientists have spotted something that should not be there. Beneath the South Atlantic Anomaly, deep at the boundary where the molten outer core meets the rocky mantle, magnetic field lines are doing something they shouldn't. They're going backward. Normally, Earth's magnetic field flows in a predictable pattern. Field lines emerge from the core in the southern hemisphere and loop around to dive back in near the northern hemisphere. It's been that way for thousands of years. A clean, organized system. A planetary engine humming along in its expected rhythm. But beneath the southern Atlantic, something has broken that rhythm. Scientists call them reverse flux patches, pockets where the magnetic field lines, instead of emerging outward, plunge straight back into the core, as if the planet has developed magnetic potholes, localized regions where the shield is essentially flowing the wrong way. This finding comes from the Swarm satellite data, analyzed at the Technical University of Denmark. Professor Chris Finlay explained it to the European Space Agency. Beneath the anomaly, his team has tracked one of these reverse flux patches moving westward across the African region. As it migrates, it eats away at the local magnetic strength. The patch acts like a drain in a swimming pool. Wherever it goes, the surrounding field weakens dramatically. This is confirmed by years of satellite observation, not theory, measured. Picture it as a bathtub full of water swirling toward a drain. Now imagine someone has cut a second hole in the bottom of the tub, and water is starting to flow upward through the new hole instead. The whole system gets confused. Pressure changes, currents shift. The water level drops faster in some places than others. That's what's happening to the magnetic field above the South Atlantic right now. What's causing these reverse flux patches? Scientists point fingers at a buried monster. About 1,800 miles beneath Africa, deep inside the mantle, there is a colossal blob of dense rock. Geologists call it the African Large Low Shear Velocity Province. Think of it as a continent-sized lump of unusual material lodged near the core mantle boundary. As Earth's molten iron flows past this giant blob, the flow patterns get disturbed. The smooth circulation that normally generates a tidy magnetic field gets thrown into chaos in this one specific region. Imagine pouring water down a perfectly flat slope. Now drop a boulder into the middle of that slope. Water still flows, but it now twists and eddies and forms strange new currents around the obstacle. That's what this buried mass is doing to the molten metal below your feet, and the resulting magnetic chaos rises to the surface as the South Atlantic anomaly. Here's where it gets stranger. The patch is moving, slowly drifting westward beneath Africa. As it moves, the weakest spot of the anomaly moves with it. Future generations of children born in southern Brazil or Cape Town might grow up in a world where compass needles wobble and confuse themselves, where satellite messages drop out unpredictably, where auroras dance in skies that have never seen them before. Some scientists believe these reverse flux patches are nothing new. They argue patches have come and gone many times throughout Earth's history. Others believe what's happening now is unusual, perhaps unprecedented in modern times. The truth lies somewhere in the data still being collected. The deeper mystery is whether this regional weakening could be the spark of something far larger, because beneath the African continent, the buried blob causing all this chaos has a twin on the other side of the planet, and both of them are even stranger than scientists imagined. Imagine reaching inside the planet and finding two enormous structures the size of continents lurking near the core. Hot, dense, unlike anything else in Earth's interior, and no one knows for sure what they are. These are the superplumes. Officially, scientists call them large, low-shear, velocity provinces, a name so technical it almost hides how strange they are, but the nickname suits them. Two giant masses, roughly the size of continents, sitting on top of Earth's core, one under Africa, one under the Pacific. Together, they may be the biggest unsolved mystery hidden inside our planet. This is confirmed. Both blobs have been mapped using earthquake waves that travel through Earth's interior. When seismic waves slow down or speed up as they pass through different materials, they reveal the hidden landscape below. According to NASA's Astronomy Picture of the Day from May 2026, these structures show unusual temperatures and chemical compositions that set them apart from the rest of the mantle. How big are they? Each one rises hundreds of miles tall and stretches thousands of miles across. The African superplume alone is so massive it would dwarf any mountain range on the surface. If you could somehow lift it up and place it on the ground, it would tower over Mount Everest by a factor that's hard to picture. These aren't just big, they're geological titans hiding in plain sight. Where did they come from? Nobody knows. But scientists have two leading theories, and both are wild. The first theory says these blobs are ancient debris. Roughly 4.5 billion years ago, a Mars-sized planet called Theia smashed into the early Earth. The collision was so violent that it ripped off enough material to form the Moon. Some researchers believe pieces of Theia sank deep into the molten Earth and never fully mixed with our planet's interior. According to this idea, the blobs are tombs, frozen graveyards of an alien world that collided with us long before life existed. The second theory is just as remarkable. Earth's surface is broken into tectonic plates that grind against each other, and at certain edges, one plate slides under another. This is called subduction. Over billions of years, ancient ocean floors have been pulled down into the mantle. The blobs, this theory says, are massive stockpiles of these old, sunken plates, a graveyard of vanished oceans, piled up at the bottom of Earth's interior. Either way, the implications are enormous. These superplumes seem to influence volcanism on the surface. Hawaii, with its long chain of fiery islands, may exist because a plume rising from one of these blobs is melting through the crust above. Iceland's geysers and lava fields may be tied to similar deep earth machinery. The idea that island chains and supervolcanoes are echoes of structures buried near the core changes how we see our planet entirely. But there's a darker possibility. The same blob beneath Africa is the prime suspect for distorting the magnetic field above the South Atlantic. If two anomalies the size of continents can warp Earth's magnetic shield from below, then the surface we walk on isn't just a calm crust over a hot ball of metal. It's the thin skin of a planet wrestling with monsters in its depths. And those monsters aren't sitting still. The flow of molten iron around them is changing. Their influence on what happens above is shifting, which leads to perhaps the most disorienting fact of all. The very speed at which our planet spins is no longer reliable. On July 9th, 2025, you lived through one of the shortest days in modern human history. You probably didn't notice. The sun rose. The sun set. Your watch ticked through the usual 24 hours. But the planet itself completed its rotation faster than expected, by about 1 1/3 milliseconds. According to the International Earth Rotation and Reference Systems Service, this was the shortest day ever recorded since modern atomic timekeeping began in the 1960s. A millisecond sounds tiny, insignificant. But here's the thing. For thousands of years, scientists assumed Earth's rotation was very gradually slowing down. The moon's gravity drags on our oceans, creating a tidal break that's been stretching our days longer for billions of years. 200 million years ago, a day was only about 23 hours. That trend has been steady and predictable until now. Since around 2020, Earth has been doing something it hasn't done in modern records. It's speeding up. According to atomic clock data, the planet has set new short-day records repeatedly over the past 5 years. July 9th, 2025, July 22nd of the same year, August 5th. Each one shaved more than a millisecond off our standard rotation, and scientists are scrambling to explain why. This is confirmed. Measured by atomic clocks accurate to better than a billionth of a second. What's behind it? Several forces are pulling in unusual directions all at once. First, there's the moon. The moon doesn't always sit directly above Earth's equator. Sometimes it swings high above one of the poles, and when it does, its gravitational pull subtly tweaks Earth's spin. Imagine spinning a basketball with your fingers near the equator versus near the top. It speeds up when you grip nearer the poles. The same physics applies to our planet. On those record-short days, the moon happened to be at extreme high or low positions relative to Earth's equator. Second, there's the atmosphere. During summer, the jet stream slows down. The total angular momentum of the Earth and its atmosphere has to stay constant. So when the air slows, the solid planet picks up the lost speed. We rotate slightly faster. But the third factor is the strangest of all. According to geophysicist Duncan Agnew of the Scripps Institution of Oceanography, Earth's liquid core has been slowing down for about 50 years. As the core slows, the rest of the planet has to spin faster to compensate. The same conservation law that makes a figure skater speed up when they pull their arms in is now operating on a planetary scale. Connect the dots. The inner core is reversing direction. The outer core is slowing. The surface is speeding up to balance it out. Everything below your feet is shifting in synchrony, and the result trickles up to your wristwatch. The consequences sound minor, but they aren't. GPS satellites depend on time accurate to billionths of a second. Financial trading systems sync transactions across continents using atomic clocks, power grids, telecommunications. satellite navigation, missile guidance. Every system that depends on coordinated time depends on knowing exactly how fast Earth is spinning. If our planet keeps speeding up, timekeepers may have to do something they've never done before. Take a second away from the clock, a negative leap second, something never attempted in the entire history of modern timekeeping. That sounds harmless. It isn't. For more than 50 years, every now and then, the world has added a second to the clock. It's called a leap second. The first was added in 1972. 27 of them have been inserted since, sprinkled across the decades whenever Earth's rotation slowed enough that atomic time and astronomical time started to drift apart. The last one was added in 2016. Since then, none, because Earth, rather than slowing as expected, has been speeding up. Now the timekeepers face a question they never thought they'd have to answer. Will we need to subtract a second instead? According to Duncan Agnew, the geophysicist who has tracked these changes for years, the probability of a negative leap second happening between now and 2035 is around 40%. 40%. That's not a fringe possibility. That's nearly a coin flip on the most unprecedented act in modern timekeeping history. This sounds like a small problem. Trim a second off the clock somewhere around 2 in the morning, no one notices, and life goes on. But the engineers and physicists who maintain the world's atomic time infrastructure are quietly terrified, because removing a second has never been done before. And the systems we've built around the assumption it would never happen are everywhere. Picture the modern world running on synchronized time. Stock exchanges in Tokyo, London, and New York compare timestamps to settle trades across milliseconds. Telecommunications networks route phone calls based on precise timestamps. Power grids switch loads using time signals. GPS satellites broadcast time signals so accurate that a tiny error translates to a position error of hundreds of feet on the ground. All of it built on a single foundational rule. Time always moves forward. A negative leap second breaks that rule. 2:01 a.m. would jump straight to 2:03 a.m., skipping a second entirely. Or worse, the clock might briefly show a negative time, an impossible moment that exists between two ordinary moments. Judah Levine, a physicist at the National Institute of Standards and Technology, told reporters something chilling. When the leap second system was designed in 1972, no one ever expected a negative one would be needed. Nobody planned for it. The mathematical possibility was included only because completeness demanded it. And now that mathematical possibility is approaching reality, there's a second wrinkle. Even regular positive leap seconds, after 50 years of practice, still cause problems. Software glitches, time servers that crash, aviation systems that briefly lose track of where planes are. Major outages have been traced to mishandled leap seconds in the past decade. If a positive leap second still trips up our infrastructure, what happens when we try the opposite for the very first time? In 2022, the world's official timekeepers met at the General Conference on Weights and Measures. They made a quiet decision. By 2035, leap seconds will be retired entirely. The world will simply allow atomic time and Earth time to drift apart, accepting that the clocks on our walls and wrists are no longer locked to the spinning of our planet. Think about what that means. For all of human history, time has been measured by the rotation of Earth itself, the rising of the Sunday, the cycle of day and night. Now we are about to formally divorce our timekeeping from our planet. The reason? The planet is no longer cooperating. It is doing something unpredictable. And the next strange thing it has done is to lose its wobble entirely. For more than a century, Earth wobbled like a slightly off-balance spinning top. It was discovered in 1891 by an American astronomer named Seth Carlo Chandler. He noticed that Earth's rotation axis didn't trace a perfect line through the planet. Instead, the geographic North Pole drifted in a small circle, completing one loop every 433 days. The circle was tiny, about 30 feet across at the surface, but it was real, persistent, and as predictable as the seasons. Astronomers named it the Chandler Wobble, For 124 years, the wobble was a fixture of planetary science, as reliable as gravity, as steady as the orbit of the moon. Then, sometime around 2015, it disappeared. This is confirmed, measured by the International Earth Rotation and Reference Service, verified by years of subsequent monitoring. Researchers led by Taewon Jeon published a study in September 2025 that revealed the unsettling truth. Earth's Chandler wobble collapsed after 2015. The amplitude shrank to less than half its normal size. By 2017, the wobble was so faint that only the smaller annual oscillation remained visible in polar motion records. The 433-day signal that had defined our planet's spin for over a century had simply faded away. Picture a spinning top on a table. It always wobbles slightly as it spins, drawing tiny circles with its tip. Now, imagine those circles suddenly shrinking, then disappearing. The top is still spinning, still upright, but that little dance it always did, gone. That's what happened to our planet. The cause turned out to be something extraordinary. Jeong's team analyzed 40 years of rotation data using mathematical techniques that reveal hidden patterns. They traced the cause back to the years 2010 and 2011. During that time, a powerful La Niña event reshaped the world's water cycle. Massive flooding hit Australia and South America. Enormous quantities of water shifted from oceans onto land. By 2011 and 2012, satellite measurements showed huge anomalies in atmospheric pressure and terrestrial water storage. That redistribution of water was enough to silence the Chandler wobble. Water is heavy. When it moves from one part of the planet to another, it changes how Earth's mass is distributed. That changes the planet's rotational inertia, and in this case, it dampened the natural wobble until the signal nearly vanished. There has been only one comparable event in modern records. Between 1925 and 1940, the wobble similarly weakened and shifted phase. But back then, scientists lacked the tools to track every change in detail. This time, every shift was measured down to centimeters. The implications go beyond curiosity. Navigation satellites depend on knowing exactly where Earth's axis points. Astronomical observations rely on precise reference frames. Any sudden change in the Chandler wobble ripples through every system that needs to know its location with high accuracy. Engineers had to update their models when the wobble vanished. The rules they'd relied on for decades had to be rewritten. Here's the unsettling takeaway. A few extreme weather events, redistributing the planet's water, were enough to silence a 100-year-old planetary rhythm. If something so familiar can vanish that quickly, what else about Earth's behavior might we be missing? What else is shifting beneath the surface of our daily routines, invisible until someone with the right instruments looks for it? The answer turned out to be more disturbing than anyone expected, because while the Chandler wobble was disappearing, another part of Earth's spin geometry was already on the move, and it wasn't slowing. It was rushing. The magnetic North Pole isn't where it was when you were born. If you were born in the 1990s, the magnetic North Pole sat above northern Canada. By the early 2000s, it had begun moving. By 2020, it was roughly halfway across the Arctic Ocean, hurtling towards Siberia at a pace that stunned geomagnetic scientists. Today, it continues that dash. The pole has shifted hundreds of miles in just a few decades. This is confirmed, tracked by satellites, magnetometers, and global geomagnetic models updated every 5 years. For comparison, the magnetic North Pole moved about 10 kilometers per year through most of the 20th century. Around the year 1990, it began accelerating. By the early 2000s, it was racing across the Arctic at 50 to 60 kilometers per year, roughly 31 to 37 miles annually. Then, it sped up even more. Some years, it traveled over 40 miles. Then the pace eased somewhat after 2015, but the pole has never returned to its old leisurely drift. It's still on the move. Why? The answer lies thousands of miles below. Two great patches of strong magnetic field exist in the northern hemisphere, one over Canada and one over Siberia. These patches are connected to powerful currents of molten iron flowing in Earth's outer core. For most of recorded history, the Canadian patch dominated, anchoring the magnetic North Pole roughly above the Arctic islands of northern Canada. Then something changed. Around the late 20th century, the Canadian magnetic patch began to weaken. The Siberian patch grew stronger. Like two wrestlers struggling for control, the balance shifted. The Siberian patch won. As it strengthened, it pulled the magnetic pole toward itself, dragging it across the Arctic Ocean toward the Russian coast. Picture two giant magnets buried beneath the ice, one under Canada, one under Siberia. For centuries, the Canadian one was stronger, and the magnetic pole sat above it. But the Canadian magnet has been losing strength while the Siberian one gains power. The pole has been sliding from one to the other, gathering speed as the imbalance grows. This isn't just a curiosity for compass enthusiasts. It's a global problem. Every airport runway in the world is named based on its magnetic orientation. Air traffic control systems rely on knowing which way north points. The World Magnetic Model, used by militaries, airlines, smartphones, and submarines, has had to be updated unexpectedly because of the pole's behavior. In 2019, the model was updated a year ahead of schedule because the pole was moving so unpredictably that the existing version had become inaccurate. That had never happened before. Compasses have started lying. In some regions of the high Arctic, people have noticed their handheld compasses drifting away from where they used to point. Animals that navigate by Earth's magnetic field, like sea turtles and migratory birds, may be subtly affected. Some research suggests changes in magnetic patterns can influence animal migration routes. Scientists associate the pole's mad dash with broader changes deep in the core. The same molten currents that produce reverse flux patches over the South Atlantic appear linked to the patches strengthening and weakening near the northern hemisphere. Earth's magnetic engine, in other words, is rebalancing itself. What happens next? Some scientists worry the pole's shift could be a precursor to a magnetic field reversal. Others insist it's a normal fluctuation in the geodynamo. The data is too new to know. What's certain is that the planet is restless. And as if the inner workings shifting weren't enough, the skies above us have begun raining fire. In the first 3 months of 2026, Earth waded through what astronomers call a shooting gallery. Across America, Europe, and Asia, witnesses reported a wave of brilliant fireballs streaking across the sky. Some lit up the daytime, others triggered sonic booms, a few shattered windows. According to a report from the American Meteor Society, something has shifted in the rate at which large rocks are slamming into our atmosphere. Mike Hankey, the researcher who manages fireball reporting tools for the Society, analyzed data going back to 2011. After years of stable activity, he wrote in the official report, something appears to have shifted. The signal is consistent across multiple metrics. This is confirmed by tracking data, not anecdote, documented across the agency's monitoring systems. What changed? 2 things stand out. First, fireballs have doubled in activity from a specific zone of space called the Anthelion. This is the region directly opposite the Sun from Earth's perspective. Objects coming from this direction are essentially catching up to us from behind as they fall deeper into the inner solar system. Historically, the Anthelion zone has produced a few fireballs per year. In early 2026, activity from this slice of sky doubled. Nearly 10 major fireball events came from a single 1,000 square degree patch of the Anthelion zone in just 3 months. Second, scientists noticed an unusual spike in meteors from what they call high declination radiants. These are rocks moving on steeply tilted orbits, almost vertical compared to the flat plane of our solar system. That's deeply strange. Most space debris orbits the Sun in roughly the same plane. Rocks coming in at steep angles suggest they originated from somewhere unusual, a disrupted comet, a recently shattered asteroid, or something we haven't identified yet. Picture our solar system as a giant flat dinner plate. Most of the rocks orbit along the surface of that plate, like marbles rolling around a flat table. Now imagine marbles suddenly dropping straight down from above the table, hitting the plate from steep angles no one expected. That's what these high-declination meteors look like to astronomers. Cosmic visitors from outside the normal traffic lanes of our solar system. Could it be a new meteor shower? Probably not. Predictable showers like the Perseids happen when Earth crosses the dusty trail left by a known comet. We can predict those down to the hour. This new wave doesn't fit any known parent body. It's not following the schedule of any familiar comet. Whatever is dropping these rocks on us, we haven't found it yet. Some researchers wonder if AI chatbots might explain part of the apparent surge. People who see a fireball might now ask ChatGPT or similar tools where to report it and end up routed to the American Meteor Society. That could inflate witness counts. But chatbots cannot explain physical phenomena. They cannot generate sonic booms. They cannot trigger satellite lightning detectors. They cannot punch holes through houses in Texas. The physical evidence of the surge is real. In the first 3 months of 2026 alone, the Society logged 2,046 fireball events. The numbers may not look dramatically higher than past years on paper, but the size of the rocks and the energy they released has shifted. We're not getting more sand grains burning up. We're getting bigger pieces, more often, hitting the ground in some cases. And one of those rocks chose to detonate over an American city. Imagine a region of space directly behind Earth, opposite the Sunday, a blind spot in our solar neighborhood where rocks creep up from behind us as they fall inward. This is the Anthelian zone, and in 2026, it has begun producing fireballs at twice its normal rate. To understand why this matters, picture Earth's path around the Sunday. Our planet sweeps through space at about 67,000 miles per hour. The space directly opposite the Sun, behind us along this orbital path, is a special zone. Objects moving slower than Earth in similar orbits get caught up to from behind. Picture a highway where a faster car catches up to a slower one in the next lane. That's roughly what happens with Anthelian meteors. They're not crashing into us head-on. They're being overtaken. Historically, this zone produces a quiet, steady stream of fireballs, maybe a few notable ones each year. According to American Meteor Society data, that pattern held for more than a decade of careful tracking. Then, early 2026 broke the rhythm. In just 3 months, nearly 10 major fireball events emerged from a single 1,000 square degree patch of the Anthelian zone. To picture what that means, imagine looking at the night sky through a frame about 32 degrees on each side. That single patch produced almost as many large fireballs as the whole zone usually delivers in a full year. This is confirmed, documented in the Society's official report. The zone's most dramatic event happened on March 9, 2026. A fireball blazed across the eastern seaboard of the United States. 282 witnesses filed reports. The flash was visible from California to Germany, or at least, fireballs from this same general source appeared across continents within the same time window. A coordinated wave of cosmic debris hitting Earth from a single patch of sky. Scientists are scrambling to identify the source. Predictable meteor showers happen when Earth crosses the dust trail of a known comet. The Perseids, the Geminids, the Leonids. Every August, every December, every November, the dust trails are mapped. The parent bodies are catalogued. The Anthelian surge fits no such pattern. That leaves a few possibilities. The first is that a previously unknown comet has recently broken apart, releasing a new debris stream that Earth is now plowing through. The second is that an asteroid has shattered, scattering fragments in our path. The third possibility is more unsettling. The objects might be coming from beyond the solar system. Interstellar visitors slipping through our cosmic neighborhood, perturbing the local dust into our path. Whatever the source, the data points to a glaring blind spot in our planetary defense. According to the American Meteor Society report, Scientists are relying heavily on crowdsourced eyewitness accounts to calculate where these rocks come from. When the 7-ton asteroid exploded over Ohio, the only sky camera in the entire state was offline. We are literally hoping people with smartphones happen to look up at the right moment. This blind spot becomes critical when you consider what really lurks in the Anthelian zone. Some rocks in that direction are coming from orbits that take them dangerously close to Earth's path. We know about the big ones, the kilometer-scale asteroids that get tracked by NASA, but the smaller ones, the city-killer-sized rocks, mostly slip past unnoticed until they're hours from impact, or, in one case, until they hit a roof. On a Saturday afternoon in March 2026, a piece of the early solar system smashed through the roof of a home in North Houston. The rock was about the size of a baseball. It had been traveling through space for over 4 billion years, drifting between the orbits of Mars and Jupiter, until something disturbed its trajectory and sent it falling toward Earth. About 30 miles above the city, the meteor broke apart. The energy released equaled 26 tons of TNT. Witnesses across Texas reported a flash brighter than the sun and a sonic boom that rattled windows for miles. One fragment, dark and jagged, did not burn up. It survived the descent through the atmosphere, slammed through the roof of a home, ricocheted around a bedroom like a cosmic pinball, and finally came to rest somewhere inside the house. The family was unharmed. The roof was not. This is confirmed, documented by the American Meteor Society and reported by media outlets across the country. Picture the scene: a quiet Texas suburb on an ordinary weekend. Birds in the yard, cars in the driveway. Then, without any warning, a piece of an ancient asteroid punches through the ceiling of a bedroom and bounces around like a cannonball. The original mass of the rock that entered the atmosphere weighed about 1 ton, most of it vaporized. But a fragment about the size of a softball survived to ground level, and that fragment chose, by pure chance, to find a roof in North Houston. This isn't unprecedented. Meteorites have struck buildings before. A famous case involved a meteorite that hit a woman in Alabama in 1954 while she napped on her couch. Another famously crashed through the trunk of a car in upstate New York. But the frequency of these events is rising along with the broader fireball surge. The Houston meteor is part of a pattern, not an outlier. A few weeks later, an even larger event happened over Ohio. A 7-ton asteroid exploded high in the atmosphere. The flash was seen by hundreds of witnesses. The sonic boom was picked up by lightning detection satellites. Scientists tried to trace the rock's trajectory to figure out where it came from and where any surviving fragments might have landed. They hit a wall. The only weather-grade sky camera in the entire state of Ohio that was set up to track this kind of thing was offline that day. The American Meteor Society had to rely entirely on eyewitness reports, smartphone videos, doorbell camera footage, people who happened to be looking the right direction at the right moment. From this patchwork, they pieced together a rough trajectory, but the precise impact zone was never confirmed. Somewhere in Ohio or beyond, fragments of a 7-ton space rock are still lying on the ground, undiscovered. Mike Hankey, the society researcher who leads fireball tracking, summed up the problem in his report. After years of stable activity, something appears to have shifted. The signal is consistent across multiple metrics. In other words, this is real, this is measured, and it's happening fast enough that our existing infrastructure can't keep up. The blind spot is enormous. There are only a handful of full-sky monitoring cameras across the United States. Most of them are operated by volunteers. Some are decades old. Most of the night sky over most of the country is essentially unwatched by automated systems. We are relying on luck and crowdsourcing to track objects falling from space. And these objects, increasingly, are big enough to do real damage. If you think falling rocks are the only outside force changing Earth right now, listen to what the sun has been doing. Scientists have proposed something that sounds like science fiction. Solar flares might be triggering earthquakes. According to research published in February 2026, and reported by Science Daily, a team of researchers has uncovered a surprising connection between the sun's tantrums and seismic activity deep in Earth's crust. When solar flares hit the upper atmosphere, they disturb the ionosphere, the electrically charged layer of air far above your head. That disturbance generates electric fields. Those electric fields can penetrate down into Earth's surface, all the way to fragile fracture zones in the crust. And if a fault is already on the verge of slipping, the surge of electric energy might be the final nudge that sets off an earthquake. This is currently a theory, not confirmed, but the data behind it is intriguing enough that researchers are taking it seriously. Picture the chain of events. The sun ejects a burst of charged particles. They sweep across 93 million miles of space. They slam into Earth's magnetic field. Charged particles flood the upper atmosphere, generating electric currents in the ionosphere. Those currents induce voltage changes that ripple downward through the ground. Most of the time, nothing happens. The voltage just dissipates. But if there's a fault deep in the rock that's been silently building stress for years or centuries, the additional electrical jolt may push it past its breaking point. The mechanism is subtle. Faults under stress contain rock that's already on the edge of failure. Friction holds them in place. When you change the electrical state of the rock, you can change how that friction behaves, just slightly. Just enough that a fault sitting at 99% of its breaking strain might cross to 100% and rupture. If this theory is correct, it would mean Earth's surface is not isolated from the activity of the Sunday. The ground beneath you is electrically connected, in a faint but real way, to events happening across the solar system. A flare on the surface of the sun, 8 minutes of light travel away, might be subtly tied to whether a fault in California or Japan releases its energy today or tomorrow. The implications for earthquake prediction are huge. If solar activity can be a trigger, then space weather forecasts could become part of seismic hazard models. We already monitor solar flares in real time. If their effects on the ground can be quantified, we might gain a new tool for warning when fault systems are most vulnerable. But the effect, if real, would also be unsettling. It would mean Earth is more responsive to external influences than scientists have traditionally assumed. The crust we walk on isn't just a passive layer. It's a vast electrical conductor, sensitive to currents from above. The timing of this research is striking. The sun is currently in an active phase of its 11-year solar cycle. Major flares have erupted multiple times in the past few years. Auroras have appeared at strange low latitudes, far from the polar regions where they normally dance. Power grids have been put on high alert. Satellite operators have moved spacecraft into safe mode to protect them from radiation surges. If solar flares can shake the ground, then everything about our relationship with the sun changes. The star at the center of our solar system isn't just a source of warmth and light. It's a planetary force that may, in subtle ways, be tied to the very stability of the rocks beneath our feet. And while researchers debate that link, an even stranger object has slipped into our solar system, one that nobody can fully explain. In the past few years, an interstellar visitor has been gliding through our solar system. Astronomers gave it a sterile name. We'll just call it the Visitor. This visitor is the third confirmed interstellar object ever observed. The first was Oumuamua in 2017, a strange cigar-shaped rock that vanished before scientists could fully study it. The second was Borisov in 2019, a comet from another star system. The third arrived in 2025 and is still being tracked. According to a March 2026 article by Avi Loeb, an astrophysicist at Harvard University, this third visitor has demonstrated 22 anomalies that defy conventional explanation. This is mostly theory. Loeb's interpretations are controversial. Other scientists believe most of these features can be explained by natural processes, but the anomalies themselves are documented. The debate is over what they mean. Let's walk through some of the most striking. On January 22, 2026, the visitor lined up with the Earth-Sun axis to within 0.69 degrees. At that exact moment, its tail of ejected material pointed directly at our planet. The probability of such a precise alignment by chance is staggeringly low. The object came from a direction in the sky almost identical to where the famous WOW signal originated in 1977. The WOW signal was an unusually strong narrowband radio burst that has never been explained. The visitor's incoming trajectory matches that signal's source to within 9 degrees of arc. The probability of this happening by random chance, according to Loeb's calculations, is around 0.6%. When astronomers processed 40 Hubble Space Telescope images of the visitor using a technique that filters out the symmetric glow around its nucleus, they found something remarkable. 3 thin jets of material emerging from the surface, separated by exactly 120 degrees of arc from each other. 3 jets, perfectly symmetric, the kind of pattern you might expect from technological thrusters arranged for stability. Or, scientists insist, from sublimation of 3 pockets of ice on a rotating rock. Picture a rock the size of a small mountain, hurtling through the solar system at speeds faster than any comet ever observed. Now picture 3 thin streams of gas blasting from its surface in perfect geometric arrangement, like the exhausts of some unimaginable craft. Then picture the same rock pointing its tail at Earth on a date when it perfectly aligns with our orbit. Whatever you call this object, it is not behaving like ordinary debris. The visitor's nucleus is more massive than the previous 2 interstellar objects combined. It's moving faster than either of them. Near its closest approach to the Sun, it brightened more rapidly than any known comet, and it appeared bluer than the Sun itself. Most comets get redder as they approach perihelion. This one did the opposite. Then there's the polarization. Comets reflect light in characteristic ways. Astronomers measure this through polarization. The visitor has shown extreme negative polarization, unprecedented for any comet in the historical record, including Borisov. By March 16, 2026, the visitor passed close to Jupiter and began heading out of our neighborhood. As of this writing, it is fading. Soon, it will be too faint to study. We may never get another close look at it. For most scientists, the explanation is purely natural. Strange rocks from other stars are simply different from local rocks. Their anomalies reflect different chemistry, different formation conditions, different journeys through the cold of interstellar space. For a smaller group of researchers, including Loeb himself, the cluster of 22 anomalies is enough to seriously consider another possibility, that this object is not a rock at all, that it's something built. He emphasizes this is a hypothesis, but he argues the data warrants taking the hypothesis seriously. Whatever this visitor was, its arrival coincides with an era of unusual planetary changes on Earth. And the next change is happening in the cold waters of the North Atlantic. In a world where almost every ocean and continent is heating up, one patch of sea has stubbornly stayed cold for more than a century. It sits south of Greenland, between Iceland and Newfoundland, while the rest of the planet warms by record-shattering amounts each year. This patch has gotten slightly colder. Climate scientists have known about it since the 1900s. It shows up in temperature maps as a deep blue blot in a sea of red. They called it the cold blob. For a long time, nobody could explain it. Some researchers blamed atmospheric pollution. Others suspected ocean currents. The debate raged for decades. Then, in 2025 and 2026, a team from the University of California, Riverside, cracked the mystery. According to research by Kai-Yuan Lee and Wei Liu, only one explanation fits both the temperature and salinity patterns observed in the cold blob over more than 100 years of data. The Atlantic Meridional Overturning Circulation, the Great Ocean Conveyor Belt, is slowing down. This is confirmed. The science underlying it has been peer-reviewed and replicated across multiple independent climate models. The conveyor belt, often called the AMOC for short, is one of the largest and most important ocean current systems on Earth. Warm, salty water flows north along the surface from the tropics toward the Arctic. As it cools, it gets denser. Denser water sinks. The sinking water then flows back south along the deep ocean floor, completing a vast circulation pattern that spans the entire Atlantic. This circulation is what makes northern Europe much warmer than its latitude would suggest. Without it, London would feel more like Labrador. When the conveyor belt slows, less warm water reaches the North Atlantic. The cold patch south of Greenland gets cooler. Salinity drops because less salty tropical water is arriving. Both signals show up in the data exactly as the conveyor weakens. The implications stretch far beyond a chilly patch of ocean. The AMOC is what regulates rainfall patterns across Europe, North America, and Africa. It influences the position of the jet stream, the high-altitude air current that steers weather systems across the northern hemisphere. It affects where tropical storms form and how strong they grow. Picture the AMOC as a planetary heart pump, warm blood up, cold blood down. The whole climate of the northern hemisphere depends on the steady beat of this circulation. If the heart slows, every organ feels the effects. Crops in Europe, fisheries in Greenland, hurricanes in the Caribbean. Everything is connected through this single current system. The researchers found that the cooling has been intensifying, not just persisting, getting stronger. That suggests the slowdown isn't ancient history. It's current, it's happening now, and it's accelerating. Climate scientists have argued for years about how stable the AMOC really is. Some models showed it could collapse abruptly under certain conditions. Other models suggested it would weaken slowly and gradually. The cold blob study tilts the evidence towards something more concerning. The system has clearly been weakening for over a century, and the rate appears to be increasing. The next question is the one nobody wants to answer. How close is the conveyor belt to a full collapse? Because if it does collapse, the consequences would not be subtle. They would reshape the climate of the entire northern hemisphere within a single human lifetime. And the latest research suggests the warning signs may already be flashing. If the Atlantic conveyor belt collapses, life across the northern hemisphere changes fast. According to research published in 2023 by Peter and Suzanne Ditlevsen, statistical analysis of long-term ocean data suggests the AMOC may collapse somewhere around the year 2057, with a possible range stretching from 2034 to 2128. That's the headline. A peer-reviewed study placing a possible date on a continent-altering event. This is theory built on data, not certainty, but the data behind it is robust enough that it has triggered serious concern in climate science circles. What does collapse mean here? Not the ocean stopping entirely. The conveyor belt would slow down so dramatically that its heat transport function would essentially shut off. Models suggest that could happen in as little as a few decades once the system passes a tipping point. After that, the climate of the northern hemisphere would shift abruptly. Air temperatures over the North Atlantic could drop by 1 to 3 degrees Celsius on average, with regional cooling near Greenland and northern Europe potentially reaching 8 degrees Celsius. To put that in context, 8 degrees Celsius cooler in winter would push parts of the United Kingdom and Scandinavia into climates resembling parts of Siberia. The growing seasons across northern Europe would shorten dramatically. Crops adapted to mild Atlantic weather would fail. Heating bills would soar. Billions of dollars worth of agricultural infrastructure would have to be rebuilt around colder norms. But it gets worse. A weakened conveyor belt would shift the global rain patterns in dramatic ways. The tropical rain band, called the Intertropical Convergence Zone, would migrate southward. That migration could trigger massive droughts in the Sahel region of Africa, where hundreds of millions of people depend on rainfall agriculture. Sea levels along the eastern seaboard of North America could rise by up to 80 centimeters because of changes in ocean dynamics, swamping coastal cities like New York, Boston, and Miami beyond what current sea level projections show. How would we know if it's coming? researchers have been hunting for early warning signals. In a 2026 paper published in Communications, Earth and Environment, scientists at Utrecht University in the Netherlands ran ultra-high-resolution simulations of the Atlantic. They added fresh water to the model to mimic melting Greenland ice. Then they watched what happened to the Gulf Stream. The result was striking. As the AMOC slowed, the Gulf Stream reached a tipping point of its own. It abruptly jumped north by 219 kilometers, about 136 miles, in just 2 model years. That dramatic shift occurred about 25 years before the full AMOC collapse in the simulation. In other words, a sudden northward jump of the Gulf Stream may be a warning siren. 25 years before the conveyor fails completely. The team then compared their simulation to the real world. They examined satellite data from the past 30 years and deep-sea records going back to 1965. The early hints of similar behavior, they reported, may already be visible in the observations. Subtle, not yet conclusive, but they're there. So, is the Gulf Stream actually starting to jump? Some studies say yes. Others urge caution. The signal is faint, the data is noisy, and the consequences of being wrong in either direction are huge. False alarm and you cry wolf. Missed alarm and you watch a continent freeze. The honest answer is that we don't know how close we are. What we do know is that the cold patch is intensifying. The conveyor is weakening. The Gulf Stream is acting strange. And ice is melting faster than predicted. Every signal points the same direction. While the ocean shifts, the very land beneath us is moving too. Earth's North Pole has been drifting east. Not the magnetic pole this time, the geographic pole, the actual axis of rotation, the point in the Arctic that all longitude lines converge upon. Since around the year 2000, that point has been quietly moving east, away from the spot it occupied for most of the 20th century. According to research published in 2013 and updated since, the cause is melting ice. This is confirmed, measured by satellite-based observations of Earth's gravity field and rotation axis. How can melting ice move a planet's axis? The answer comes from one of the most beautiful laws of physics: conservation of angular momentum. When mass is redistributed on a rotating body, the rotation axis shifts to balance the new mass distribution. A figure skater pulls in their arms and spins faster. Earth gains weight in one place and loses it in another, and the axis adjusts. For thousands of years, Greenland and Antarctica held huge masses of ice locked in place. That ice was a fixed feature of Earth's mass distribution. Then the climate began to warm. Greenland's glaciers started losing tens of billions of tons of ice every year. Antarctica's ice shelves began breaking off. All that water flowed into the oceans, where it spread out across the entire globe. In effect, the planet shifted weight from the high latitudes to the equator, from the poles to everywhere else. According to Clark Wilson, a geophysicist at the University of Texas at Austin, when you take this much mass from one region and move it to another, you change Earth's moment of inertia. The planet must rebalance. The spin axis moves. The shift is small in human terms. The geographic pole has moved by roughly 45 centimeters since 2000, about 1.5 feet. But the speed of the shift has accelerated, and the direction is consistent. Earth is responding to the loss of polar ice in a measurable, predictable way. It gets stranger. According to a 2025 study reported by The Travel, soil moisture loss is also playing a role. Droughts on land have caused water tables to drop. As soil dries out and groundwater is pumped up and eventually flows into the sea, more mass shifts from continents to oceans. Even agricultural irrigation patterns, drying out aquifers in the central United States, India, and elsewhere, are nudging the axis of our planet. Picture what this means. Decisions about whether to drill another well in California, whether to leave the lawn watered in a hot summer, whether to build dams or let rivers run free. All of these activities, multiplied by billions of humans across decades, are large enough to physically shift the axis of the Earth. humanity has become a geological force on a scale that affects the rotation of the planet itself. Professor J. Famiglietti, a hydrologist who co-authored some of this work, told the BBC that pumping groundwater to relieve droughts often leads to more severe long-term problems. Aquifers don't refill quickly. Once the water is gone, it's gone for human timescales. And meanwhile, every gallon pumped from underground and delivered to a thirsty city or field is a tiny push on Earth's axis. The trend is expected to continue. As Greenland and Antarctica continue to lose ice, as droughts spread, as groundwater extraction increases, the pole will keep drifting. Some climate models suggest the changes could become large enough to interfere with high-precision navigation systems within decades. The planet is reshaping itself around our actions, and the next chapter of that reshaping is happening high above the surface, in a layer of air most people don't even know exists. About 60 miles above your head, the sky becomes something else. Below that altitude, the air behaves like ordinary air. Molecules of nitrogen and oxygen jostling around. Above it, things change. Solar radiation strips electrons from atoms, creating a layer of charged particles that conducts electricity. This is the ionosphere, and in recent years, it has been behaving in ways that have alarmed atmospheric scientists. The ionosphere is the invisible electric ceiling of our world. Without it, your radio wouldn't work. Long-distance shortwave broadcasts depend on bouncing signals off this charged layer to reach across continents. GPS signals pass through it, picking up tiny delays based on how dense the charged particles are. Power grids on the ground couple electromagnetically to currents flowing through the ionosphere far above. Aurora dance there. Meteors burn there. The northern and southern lights are direct evidence of what happens when solar particles slam into this charged layer. For decades, the ionosphere had a fairly predictable rhythm, denser during the day, thinner at night, more active during solar maximum, calmer during solar minimum. Engineers built systems around these patterns: GPS networks, radio relays, power grid protection schemes. Then something started shifting. In the past several years, the ionosphere has been responding more dramatically to space weather than expected. Solar flares that should have caused minor disturbances have instead triggered widespread radio blackouts. Auroras have appeared at low latitudes, where they almost never occur. In May 2024, during the Gannon storm, brilliant auroras were visible as far south as Texas and Mexico, places where most residents had never seen the lights in their lifetimes. This is confirmed, documented by space weather monitoring stations and reported by NOAA. Why is the ionosphere becoming so reactive? The leading suspect is the South Atlantic anomaly. When the magnetic shield is weak, charged particles from space penetrate deeper into the upper atmosphere. They affect the ionosphere from above and from below, changing its density and its conductivity. The ripple effects propagate around the entire planet, because the ionosphere is connected globally. Picture Earth's atmosphere as a layered cake. The bottom layers, where you live, are insulating. They don't conduct electricity well. The top layer, the ionosphere, is essentially a giant electrical wire wrapped around the planet. Now, imagine pinching one part of that wire. The electrical behavior changes everywhere, not just at the pinch point. The South Atlantic anomaly is a region where space weather can interact more directly with the ionosphere because the magnetic shield is weak there. The disturbance ripples globally. The implications for technology are large. GPS errors during major space weather events have grown. Airline routes near the poles have been rerouted multiple times to avoid radiation exposure. Satellite operators have lost spacecraft, including the famous incident in February 2022 when SpaceX lost 40 Starlink satellites to a moderate geomagnetic storm. The ionosphere swelled, drag on the satellites increased, and they fell back into the atmosphere before they could reach safe orbits. Looking ahead, the Sun is currently in a peak phase of its 11-year activity cycle. Major flares are still erupting. solar storms are still slamming into our planet. And with the magnetic shield weaker over the South Atlantic, the upper atmosphere is more vulnerable than it's been in living memory. The sky above you is electrified, restless, and changing, and the lights it has begun to show are a warning of something stranger still. In May 2024, people in Mexico looked up and saw something impossible: green and red curtains of light dancing across the sky. Auroras, hundreds of miles south of where auroras should ever appear. The same night, residents of Texas, Florida, and even Cuba reported the same thing. Photographs flooded social media. Children saw the northern lights for the first time without ever leaving home. The event was caused by a powerful geomagnetic storm called the Gannon Storm, named after a NASA scientist who had passed away earlier that year. It became one of the most widely witnessed auroral events in modern history. This is confirmed, documented by NOAA, photographed by millions of people, and recorded by space weather instruments worldwide. Auroras happen when charged particles from the sun slam into Earth's upper atmosphere and excite the gas molecules there. The collisions release energy in the form of colored light. Oxygen produces green and red. Nitrogen produces blue and purple. Normally, these collisions happen in narrow bands near the magnetic poles. The reason is simple. Earth's magnetic field channels incoming particles toward the polar regions, like water flowing into a funnel. That's why Iceland, Norway, Alaska, and northern Canada have always been the prime aurora viewing locations. So why are the lights showing up in Texas? The answer points to the same patterns we've already explored. Earth's magnetic field is weakening in places, especially over the South Atlantic. The jet stream of charged particles flowing into our atmosphere is being deflected and concentrated in unexpected ways. When a powerful solar storm arrives, more particles than usual pour through the weak spots and reach lower latitudes than they used to. Picture a leaky bucket. Most of the time, the water flows out the bottom in a single stream. Now imagine someone pokes a few extra holes in the side. Water still flows out the bottom, but new streams squirt out from the sides too. That's what happens during major geomagnetic storms when the magnetic shield is weak. Charged particles, which normally stay near the poles, leak into mid-latitudes and even tropical zones. The Gannon storm of May 2024 was rated G5, the highest level on the geomagnetic storm scale. It was the strongest such storm in over 20 years. But what made it remarkable wasn't just its strength, it was how widespread the effects became. Auroras in places that hadn't seen them in centuries. Power grid disturbances across multiple continents. GPS errors of tens of meters. Radio blackouts on the sunlit side of Earth. A second major storm in October 2024, called the Mother's Day Plus storm by some scientists, repeated the pattern. Auroras visible far south. Power grid alerts in Sweden and South Africa. Satellite drag increases. The sun, currently near the peak of its 11-year cycle, has been reminding us how powerful it can be. Here's the unsettling part. These storms are still relatively modest by historical standards. The famous Carrington event of 1859 was much stronger. It set telegraph lines on fire and produced auroras visible from the equator. If a Carrington-level storm hit today, with the magnetic shield weaker than it was a century ago, the consequences would be catastrophic. Continental-scale power outages, global communications disrupted, satellite networks crippled, trillions of dollars in damages. The auroras dancing in unexpected places are beautiful. They're also a warning. They tell us that our protective shield is letting in things it didn't used to let in. And the question that lurks behind every recent geomagnetic anomaly is the one nobody wants to confront. Could this be the start of a complete magnetic reversal? Earth's magnetic field has flipped before, many times. North becomes south, south becomes north. Compasses spin, animals lose their navigation. The polarity of the entire planet inverts. This isn't speculation, it's geological history written in the rocks. When molten lava cools and solidifies, The iron particles inside it line up with the magnetic field that exists at that moment. Those particles freeze in place, creating a permanent record. By examining ancient lava flows around the world, scientists have mapped a complete history of magnetic reversals stretching back hundreds of millions of years. This is confirmed. The geological record is unambiguous. The last full reversal happened about 780,000 years ago. Scientists call it the Brunhes-Matuyama reversal. Before that, reversals occurred roughly every 200,000 to 300,000 years on average. Though the timing is irregular, some periods had reversals every 100,000 years. Other periods went millions of years without flipping. The pattern is chaotic, driven by complex flows in the molten outer core. We are currently overdue for a reversal by typical standards. Some scientists argue this means a flip is approaching. Others insist that magnetic reversals don't follow a clock and that being overdue means nothing. The debate is ongoing. What would a reversal look like? It wouldn't be sudden. The process takes between 1,000 and 10,000 years. During the transition, the magnetic field weakens dramatically. North and south poles split into multiple poles scattered around the planet. Compasses become unreliable. Auroras appear in random places worldwide. Eventually, after centuries or millennia of chaos, a new polarity establishes itself and stability returns. But the weakened state during a transition would be the dangerous part. Right now, our magnetic field protects us from cosmic radiation and the solar wind. During a reversal, that protection might drop to as little as 10% of normal. Cancer rates from increased radiation could rise. The atmosphere itself could be slowly stripped away if the weakening lasted too long. Satellites would be at constant risk. Astronauts would face deadly radiation doses. Some species that navigate by the magnetic field, like sea turtles, salmon, and migratory birds, could face mass disorientation and population collapse. So, is the South Atlantic anomaly the start of a reversal? Some researchers think so. They point to similar regional weakening patterns that may have preceded past reversals. Others argue that the anomaly is simply a normal fluctuation that happens periodically without leading to a flip. Many regional weakenings throughout history have come and gone without triggering a global reversal. The honest scientific answer is that we don't know. According to Science Alert, the latest analyses suggest the South Atlantic anomaly may not be a precursor to a reversal, but the same data shows the field is weakening overall and the regional anomaly is growing. Even if a full reversal isn't imminent, partial weakening could still affect our infrastructure and our biosphere. Picture the magnetic field as the immune system of our planet. It deflects, absorbs, and scatters threats from the cosmos. A weakening immune system doesn't mean an immediate fatal illness. It means more vulnerability, more chances for things to go wrong. Solar flares hit harder. Cosmic rays penetrate deeper. The atmosphere takes more damage. For now, the field still works. Compasses still point north. Birds still migrate. But the long-term direction is clear. Earth's magnetic shield is in a phase of unusual change. Whether that change builds toward a full reversal or settles back into stability is one of the great open questions of modern geophysics. And while scientists debate the future, satellites in orbit are already feeling the present. In low Earth orbit, where most of our communications, weather, and navigation satellites circle the planet, something has changed. The South Atlantic anomaly has become a hazard zone. Every time a satellite crosses through the anomaly, it enters a region where Earth's magnetic shield is weakest. Cosmic radiation penetrates deeper here than anywhere else. Charged particles from the sun get closer to the surface than usual. For sensitive electronics, this radiation is poison. This is confirmed. Documented by every major space agency and satellite operator that flies hardware through the affected region. The Hubble Space Telescope, that priceless instrument floating about 340 miles above Earth, has a strict protocol for the anomaly. Its sensitive instruments are temporarily shut down whenever it crosses the zone. Otherwise, the radiation would corrupt scientific data and potentially damage the detectors. Hubble loses up to 15% of its potential observation time because of this. Imagine the most powerful telescope humanity has ever built, forced to close its eyes for a portion of every orbit because the magnetic shield can't be trusted there. The International Space Station encounters the anomaly multiple times a day. Astronauts have reported strange flashes of light when their eyes are closed during these passes. Those flashes are not dreams or hallucinations. They are cosmic rays slicing through the eyeball and stimulating the optic nerve. Each flash represents a high-energy particle slamming into the body of an astronaut. Over months in space, the cumulative radiation dose adds up significantly. For unmanned satellites, the hazard is technical. Memory chips can have bits flipped by passing cosmic rays. Single event upsets, scientists call them. A bit that was supposed to be a 0 becomes a 1. A command that was supposed to execute correctly executes incorrectly. Most of the time, the satellite's software detects and corrects these errors. Sometimes the errors cascade. Several spacecraft have suffered serious malfunctions or even total failures while passing through the anomaly. In February 2022, SpaceX learned this lesson dramatically. A relatively modest geomagnetic storm hit Earth shortly after a Falcon 9 rocket deployed 40 new Starlink satellites into low orbit. The storm warmed and expanded the upper atmosphere. Drag increased. The satellites, not yet at their final altitude, encountered too much resistance and could not climb higher. All 40 eventually fell back to Earth and burned up. Tens of millions of dollars of hardware lost in a single storm. Now picture the future. Tens of thousands of satellites are being launched. Mega constellations like Starlink, Kuiper, and others plan to expand to over 100,000 satellites in the coming decade. All of them must traverse the South Atlantic anomaly, with all the radiation hazards that come with it. As the anomaly grows, more time will be spent inside the danger zone. More radiation hits, more single event upsets, more gradual degradation of electronics. Some operators are responding by hardening their hardware, adding shielding, building in more redundant systems, using radiation-tolerant components designed for deep space, not just low Earth orbit. But hardening costs money. It also adds weight, which makes launches more expensive. The economic pressure to keep satellites cheap conflicts with the engineering pressure to make them survive a worsening radiation environment. Picture a thunderstorm sitting permanently over a stretch of busy highway. Every truck that passes through gets a little wet, a little battered. Most make it through fine. A few suffer accidents. The longer the storm sits there, and the bigger it grows, the more accidents occur. That's the South Atlantic anomaly today. A growing electromagnetic storm zone over a critical orbital highway. And the storm just got more complicated, because a second weak spot is forming. For most of its history, the South Atlantic anomaly has been thought of as a single weak spot. One region, one problem, one phenomenon to monitor. That has changed. According to the 2026 study, published in the journal Earth, Planets and Space, the anomaly is now developing a second internal minimum, a pocket within the pocket, a weakness inside the weakness. This is confirmed, documented by the new Global Geomagnetic Field Model based on data from European Space Agency swarm satellites and a Chinese satellite mission called CSES. The original weak spot of the South Atlantic anomaly sits roughly off the coast of Brazil, near 60 degrees west longitude. That has been the historic center of the weakening. But starting around 2018, a second region near 0 degrees longitude, much closer to the African continent, began deepening at an alarming rate. Between 2018 and 2025, the eastern minimum lost approximately 600 nanoteslas of magnetic field strength. The western minimum, the historic center of the anomaly, lost only about 200 nanoteslas in the same period, 3 times faster weakening on the eastern side. 3 times. Picture two pits in a vast sheet of fabric. The western pit has been there a long time, familiar, steadily deepening. Then a second pit appears nearby, and that one is sinking faster than the original. The fabric starts to sag in a more complex way. The whole surface gets distorted. That's what's happening to Earth's magnetic field, as the anomaly splits into multiple weakening centers. What's causing the second minimum to deepen so quickly? The same root cause as the original anomaly: reverse flux patches at the boundary between the outer core and the mantle. But the patch beneath Africa appears to be intensifying or moving in ways that affect the field above more dramatically than the patch beneath South America. Something is happening in the molten iron deep below Africa that has accelerated since around 2020. The implications are concerning for several reasons. First, two pits mean more area where satellites face radiation hazards. The geographical region of weak shielding is expanding. Second, the rapid eastern weakening may indicate the underlying core dynamics are changing more quickly than the gradual western pattern suggests. Third, the structure is no longer a simple, smooth depression. It's a complex landscape of magnetic terrain that's harder to predict and harder to model. The new global field model, called CGGM2, gives the most detailed picture we have of how this evolution is unfolding. It shows that the weakening in the eastern hemisphere continues to gain intensity, while the western hemisphere also continues to lose strength. Different regions are responding differently. The simple picture of a single anomaly evolving smoothly has been replaced by a more chaotic reality. According to the researchers behind the model, all of this paints a clear picture. Earth's magnetic field is currently in a phase of heightened internal variability. Whether this is temporary turbulence or part of a longer trend toward instability, only time and continued measurements will tell. The next generation of satellite missions will determine which. There's a deeper question lurking beneath all of this. What is happening inside Earth's outer core to generate such uneven weakening? The answer might lie in something even more strange. Recent discoveries have suggested that the core itself is in a state of matter that doesn't fit our usual categories. In December 2025, scientists made a discovery about Earth's inner core that overturned decades of textbook teaching. The inner core, that solid sphere at the center of our planet, isn't really solid in the way you imagine it. According to research reported by Science Daily, new analysis suggests the inner core exists in what physicists call a superionic state. Iron atoms remain locked in their crystal lattice, but lighter atoms, like carbon and hydrogen, flow through that lattice freely, like a liquid moving through a solid. This is theory built on advanced simulation, not yet directly confirmed by observation, since no instrument can probe the inner core. But the simulations match seismic observations in ways that earlier models could not. To picture a superionic state, imagine a sponge. The sponge itself is solid. You can hold it, you can squeeze it, but the water flows through the sponge freely. Now scale this idea down to atoms. The iron lattice of Earth's inner core is the sponge. Carbon, hydrogen, and other light elements are the water. The combined material behaves as solid in some ways and liquid in others. It's neither, and both. Why does this matter? Because for decades, scientists modeled the inner core as a simple iron-nickel alloy, mostly solid, with a clean boundary between it and the liquid outer core. The new picture is more nuanced. The inner core might be soft. It might deform under stress. It might shift shape over decades or centuries in ways a simple solid cannot. This connects to other puzzles we've already explored. Geophysicist John Vidali and his team reported evidence that the inner core's surface may be morphing. They found subtle differences in seismic waveforms recorded at stations in Alaska and Canada that couldn't be explained by rotation alone. The surface of the inner core, they argued, must be undergoing what they called viscous deformation, slowly flowing, slowly reshaping. A superionic inner core makes that easier to understand. If the boundary between the inner and outer core is a region where light atoms flow more freely, it makes sense that the boundary itself might shift in shape over time. The interaction between the soft inner core and the swirling outer core produces a complex, dynamic interface that scientists are only beginning to model. The implications are profound. The inner core isn't just a solid lump. It's an active, evolving system. Its rotation slows and reverses. Its surface morphs. Its composition allows for unusual physical behavior. Every assumption we had about the calm center of our planet has been replaced with a picture of something far more dynamic. Why should this affect you? Because the magnetic field that protects you depends on the relationship between the inner and outer cores. If the inner core is softer than we thought, if its surface is changing shape, then the boundary conditions for the magnetic field generation in the outer core are also changing. The reverse flux patches over the South Atlantic, the wandering North Magnetic Pole, the growing weak spots in the shield. All of these surface phenomena trace back to changes happening in the deep core. The deeper we look, the stranger the picture becomes. Earth is not a static rock with a fixed magnetic field. It's a living engine, rebalancing itself across timescales we can barely perceive, with inner workings made of states of matter that don't exist anywhere else in our experience. And that engine is generating consequences we can measure on the surface, including a small but important fact about how long your day actually lasts. For most of geological time, days on Earth have gotten longer. About 400 million years ago, a day was only about 22 hours. Coral fossils from that era preserved daily growth bands, and counting them shows that ancient years contained over 400 days. The reason for the lengthening is mostly the moon. Tidal friction between Earth and the moon transfers spin from Earth to the moon's orbit, slowing our rotation by tiny amounts every century. This is confirmed. The fossil record agrees with astronomical measurements. But superimposed on that long-term slowing trend are shorter cycles of variation. Some last a few years, others last decades, and some, the most mysterious, last about 70 years and appear to be linked to changes in Earth's outer core. Geophysicists have noticed that the length of a day fluctuates by a few milliseconds over decades, in patterns that match what's happening to the speed of the inner core's rotation. When the core slows down, the surface speeds up. When the core speeds up, the surface slows down. Total angular momentum stays constant. The two parts of the planet trade rotational energy back and forth across the boundary between liquid and solid. According to USC researcher John Vidale, the core has been slowing down for approximately the last 50 years. As a direct consequence, the rest of Earth has been speeding up to compensate. This is part of why the recent record short days of 2025 are happening. The core's deceleration over decades is contributing to a measurable acceleration at the surface. Picture two coupled flywheels. One is hidden inside the other. They share angular momentum through magnetic and gravitational coupling. If you slow down the inner flywheel, the outer one speeds up to keep the total constant. That's the relationship between Earth's core and the rest of the planet. The implications extend beyond timekeeping. The same processes that change day length affect weather patterns, ocean currents, and possibly even the climate. Some scientists have proposed that subtle variations in Earth's rotation can influence the position of the jet stream. Tiny changes in jet stream position can cascade into major weather pattern shifts, droughts in some regions, floods in others. The relationship between core dynamics and climate is still being explored, but the connection is real. Earth's day length, magnetic field, ocean circulation, and atmospheric patterns are all subtly linked. A change in one ripples through all the others. The challenge for scientists is teasing apart which changes are causing which. What's confirmed is the basic picture. The core is slowing, the surface is speeding up, days are shortening. The moon will eventually win this tug of war over millions of years. But over decades, the core can dominate. And right now, the core is doing something unusual enough that scientists are measuring effects on the surface, on satellites, and on time itself. This is one reason the world's official timekeepers decided in 2022 to retire leap seconds entirely by 2035. The relationship between Earth time and atomic time has become too unpredictable to maintain through traditional adjustments. Instead, the two will be allowed to drift, and we will accept that the clocks on our walls no longer track the literal spinning of our world. The deep movements of the core ripple all the way up to your wristwatch. They also ripple through the largest reservoirs of fresh water on Earth, where another shift is unfolding. Beneath the dry plains of Texas, the wheat fields of India, the orchards of California, vast underground rivers flow. They're not rivers in the cinematic sense. There are no roaring waterfalls, no fish darting through cathedrals of stone. Instead, water moves through pores and cracks in buried layers of rock, slowly, over decades and centuries. These are aquifers, the hidden circulatory system of the continents. Aquifers store more fresh water than all the lakes and rivers on Earth combined. They are the lifeline of agriculture in much of the world. They supply drinking water to billions of people, and right now, they are being drained at a pace that threatens to reshape the planet itself. This is confirmed, documented by the GRACE satellites, which measure tiny changes in Earth's gravity to track the movement of underground water. Since 2000, scientists have estimated that aquifers around the world have lost more than 2,000 cubic kilometers of water. To picture that volume, imagine filling Lake Erie almost 5 times over. All of that water has been pumped up to the surface, used for irrigation, drinking, industry, and eventually flowed into the oceans. It's gone, removed from the underground reservoirs that took thousands of years to fill. This loss is doing something extraordinary to Earth's spin. As we touched on earlier, redistributing mass on a rotating planet shifts the rotation axis. Pumping groundwater from the continents and dumping it into the oceans is exactly that, according to geophysicist Clark Wilson and his colleagues. When you take water out of the ground and move it to the sea, you change Earth's moment of inertia. The axis tilts in response. But there's more. The drying of soil and the depletion of aquifers also contribute to climate feedbacks. Less water in the ground means less moisture available to evaporate into the atmosphere. Less moisture means less cloud formation in some regions. Less rainfall, drier soils. The cycle reinforces itself, locking some areas into deeper droughts. Worldwide, the trend is concerning. The Ogallala Aquifer, beneath the central United States, one of the largest aquifers in the world, has dropped by hundreds of feet in some places since heavy pumping began in the 1950s. Parts of the high plains will likely run dry within a generation or two if current pumping rates continue. Once they're empty, regenerating them takes thousands of years of slow recharge from rainfall. In northern India, the situation is even more dramatic. Satellite data shows the region is losing groundwater at one of the fastest rates on Earth. Hundreds of millions of farmers depend on this water. Cities of tens of millions rely on it for drinking. When the wells run dry, social and economic collapse will follow. Picture an underground bathtub being emptied with a giant straw. As water comes out, the ground above can sink. The phenomenon is called subsidence. Parts of the Central Valley of California have sunk over 30 feet because of groundwater pumping. Mexico City sinks nearly 20 inches every year. The land literally collapses as the support of buried water is removed. What does all this have to do with planetary anomalies? Everything. The same redistribution of water that shifts Earth's axis also alters the loading on tectonic plates, can affect local seismic activity, and feeds back into the global climate system. Human water use has become a planetary force. We are draining a resource on a scale that influences the rotation, shape, and weather of the entire Earth. And while underground reservoirs shrink, the largest reservoirs of frozen water on the surface are also vanishing. Greenland and Antarctica together contain enough frozen water to raise global sea levels by over 200 feet if they fully melted. That's not going to happen tomorrow. It might not happen for centuries, but both ice sheets are losing mass faster than at any time in modern measurements, and the trend is accelerating. This is confirmed, documented by the GRACE satellites, ground-based ice radar surveys, and decades of glacier observations. Greenland's ice sheet has been losing about 280 billion tons of ice per year on average over the past 2 decades. To picture that, imagine a block of ice the size of Manhattan but a mile thick. That's roughly the volume of ice Greenland sheds every year. Some years are worse. The summer of 2019 saw record melting. 2023 set new records again. The pace of loss has been doubling roughly every decade, a sign that the system is not in a steady state but is responding non-linearly to warming temperatures. Antarctica is more complicated. Most of the continent is so cold that direct surface melting is rare, but the ice shelves, the floating tongues of ice that extend into the surrounding ocean, have been disintegrating. As shelves break up, the glaciers behind them speed up, dumping more ice into the sea. The Thwaites Glacier, sometimes called the Doomsday Glacier because of its potential to destabilize, has been retreating at an accelerating rate. If Thwaites collapses entirely, it could eventually contribute several feet to global sea levels. The mechanism is sobering. Warm ocean water is reaching the underside of the ice. It melts the ice from below. The grounding line, the place where the ice transitions from sitting on bedrock to floating on water, retreats inland. Once the grounding line passes a certain point, the geometry of the basin makes further retreat self-sustaining. The system runs away. Picture a giant ice cube sliding off a tilted table. As long as part of it is still on the table, friction holds it in place. Once enough slides off, gravity takes over, and the rest slides off rapidly. Some Antarctic glaciers may be approaching that geometric tipping point. The implications connect to almost every other anomaly we've discussed. Ice loss feeds the sea level rise. Sea level rise affects coastal cities. Mass redistribution from ice melt shifts Earth's axis. Freshwater released into the North Atlantic dilutes the salinity that drives the Atlantic conveyor belt, contributing to the slowdown of the AMOC. Lighter ice cover changes how much sunlight Earth reflects back to space, accelerating warming further. Not all of this is unprecedented in geological history. Earth has had many periods of warming and ice loss. What's new is the speed. Ancient ice loss events typically happened over thousands of years. The current loss is happening over decades. Civilizations evolved their cities, infrastructure, and agriculture during a stable climate window of the past 10,000 years. We built our world for the climate we had. The climate is now changing faster than our world can adapt. Researchers worry most about a few specific tipping points. The full collapse of the West Antarctic ice sheet would commit the world to about 3 meters of sea level rise eventually, regardless of what happens to emissions. The collapse of large parts of the Greenland ice sheet would add several more meters. These collapses, once started, may not be reversible on human timescales. The ice is going somewhere, and much of it is going into the sea, where it's reshaping coastlines that humans have lived on for thousands of years. In the past century, global sea level has risen by about 8 inches. That sounds small. It isn't. 8 inches of additional ocean water, spread across the entire globe, represents an immense volume of water that has shifted from land and ice to sea. This is confirmed, documented by tide gauges, going back over a century, by satellite altimeters since the 1990s, and by ice mass measurements from gravity-sensing spacecraft. The rate of rise has been accelerating. From 1900 to 1990, the rate was about 1.5 millimeters per year. Since 2000, the rate has more than doubled to over 4 millimeters per year. That doubling is huge. It means coastal communities that planned for slow change are now facing rapid change. Cities that built seawalls based on 20th century projections are finding those walls inadequate. By the end of this century, sea level could rise by anywhere from 1 to 6 feet, depending on how much ice the Antarctic and Greenland sheets shed. The high end of that range would inundate large parts of low-lying nations like Bangladesh, the Maldives, and many Pacific islands. It would force the relocation of tens or hundreds of millions of people. It would reshape the geography of major cities like Miami, New Orleans, Jakarta, Shanghai, and Mumbai. But sea level rise isn't uniform. Some coastlines are rising relative to the sea even as the sea rises. Others are sinking. Land near old glaciers is rebounding upward as the weight of ice that pressed it down lifts away. Land in places like the Mississippi Delta and parts of Indonesia is sinking due to subsidence from groundwater pumping and the natural compaction of soft sediments. The combination of rising water and sinking land can be devastating. Picture a stretch of beach where you used to play as a child. Now imagine a third of it underwater at high tide. That's already happening in places like Norfolk, Virginia. In some Pacific Island nations, entire villages have been forced to relocate inland because the salty seawater is now killing crops in fields that used to grow food. Cemeteries are being washed out. Ancestral homes are vanishing into the sea. There's another twist. The process is connected to all the other planetary changes. Greenland's melting feeds sea level rise. The melted water entering the North Atlantic can dilute the salty water that drives the conveyor belt, slowing the AMOC. A slowing amok redistributes water in the ocean in ways that can locally elevate sea levels along the U.S. East Coast, even more than the global average. Boston, New York, and Washington face elevated risk because of this oceanographic feedback. Some communities are responding. The Netherlands has long led the world in living with the sea, raising dikes and managing water flow. Singapore and Tokyo have invested billions in seawalls and flood barriers. New York City built giant berms in lower Manhattan after Hurricane Sandy. Other cities are simply hoping the worst doesn't arrive too soon. But hope isn't a strategy. The water is rising. The ice is melting. The trends are accelerating. The conveyor belt is slowing. And while the world's coastlines slowly transform, another quiet but planetary-scale process is unfolding in the frozen north. In the high latitudes of Russia, Canada, and Alaska, vast stretches of ground have been frozen for tens of thousands of years. Some places have been frozen for so long they contain the remains of woolly mammoths, perfectly preserved in the icy soil. This is permafrost, ground that stays frozen year-round, sometimes hundreds of feet deep. Permafrost covers about a quarter of the land in the northern hemisphere, and it is starting to thaw. This is confirmed, documented by ground temperature measurements at thousands of monitoring sites across the Arctic. Permafrost is more than just frozen dirt. It contains massive amounts of organic carbon, locked away in dead plants, animals, and microbes from past geological eras. As the ground warms and the ice within it melts, microbes that have been dormant for millennia begin to wake up. They start consuming the organic matter, releasing carbon dioxide and methane in the process. Methane is the warning signal. Pound for pound, methane traps about 80 times more heat in the atmosphere than carbon dioxide over a 20-year period. As permafrost thaws, methane bubbles out of melting bogs and lakes. In some Siberian regions, the gas accumulates underground, sometimes in pockets that can rupture and form craters explosively. Massive holes in the Siberian tundra, dozens of feet across, have been discovered in recent years. Scientists believe many of these are caused by methane release from decomposing permafrost. Picture a freezer full of food that's been unplugged. At first, the contents stay frozen. Slowly, they thaw, then they spoil. Bacteria that were dormant in the cold begin to multiply. The result is decomposition. The freezer of the Arctic is being unplugged by global warming, and the contents are starting to rot. The amount of carbon stored in permafrost is staggering. Scientists estimate it contains roughly 1,400 billion tons of carbon, which is about twice the amount currently in Earth's atmosphere. If even a significant fraction of that carbon is released over the coming decades, it would dramatically accelerate climate change. The release would be a feedback loop. Warmer climate thaws permafrost. Thawing permafrost releases methane and carbon dioxide. More greenhouse gases warm the climate further. Round and round. How fast is this happening? The current rate of permafrost loss is much faster than predictions made just a decade ago. Some regions of the Arctic have warmed by 2 to 3 degrees Celsius over the past few decades. Permafrost that was stable for 10,000 years is now actively thawing in a single human generation. Buildings in Russian Arctic cities are sinking and cracking as the ground beneath them softens. Roads buckle, pipelines fail. Indigenous communities that depend on permafrost for food storage and travel are losing their way of life. There's another concern. Some permafrost regions contain ancient pathogens, viruses and bacteria that have been frozen for tens of thousands of years. Most are likely harmless to modern life, but some pose risks. In 2016, an outbreak of anthrax in Siberia was traced to a thawed reindeer carcass that had been frozen since 1941. Scientists are concerned that other ancient pathogens, locked in deep permafrost, might be released as the thaw deepens. The Arctic is changing faster than almost anywhere else on the planet. The ground itself is awakening from a deep sleep. The carbon it has held for millennia is leaking into the air. The feedback loops are tightening, and the changes there ripple southward through weather patterns, ocean currents, and the lives of every person on Earth. But the Earth doesn't just change, it speaks. And the sound of those changes is louder than scientists once thought. Earth is humming, constantly, quietly, at frequencies far below the range of human hearing, but real and measurable. And that hum is changing. This is confirmed, documented by global networks of seismometers and infrasound stations. The phenomenon is called Earth's ambient seismic hum. It was first detected in the late 1990s when scientists noticed that even when no earthquakes were occurring, sensitive seismometers were picking up faint vibrations everywhere on the planet. The vibrations have a characteristic period of around 3 to 5 minutes. They never stop. They've been there as long as anyone has measured. For years, the cause was a mystery. Why does Earth hum? What makes a planet ring like a struck bell, even when nothing is striking it? The answer turned out to be the ocean, specifically ocean waves. When large waves crash against shorelines or interact with each other in deep water, they transfer energy to the seafloor. That energy travels through the rock as seismic waves. The constant pounding of waves around every coast in the world creates a continuous vibration that resonates through the entire planet. Earth is, quite literally, ringing because of the oceans. Picture a bell. If you strike it once, it rings until the vibrations damp out. Now imagine striking the bell hundreds of times per second, gently, from all directions. The bell never stops ringing. It hums continuously. That's what's happening to Earth. The oceans are striking the planet constantly. The planet is ringing constantly. And we can hear it if we know how to listen. Why does this matter to anomaly hunters? Because the hum is changing. Recent research suggests the hum may be growing slightly louder as ocean activity increases. Storms are becoming stronger and more frequent in many regions. Larger waves transfer more energy to coastlines and seafloors. The cumulative effect could be a measurable increase in the planet's background vibration. The hum also serves as a tool to study Earth's interior. By analyzing how the vibrations propagate through different layers of rock and metal, geophysicists can build maps of Earth's interior structure. The same vibrations that the oceans set off help us understand the cores, the mantles, the boundaries between layers. The hum is both a phenomenon and a probe. There's a stranger possibility. Some research suggests that human activity might be contributing to the hum. Mass infrastructure, dams, power plants, cities, and the constant pumping of water and oil from underground all create low-frequency vibrations. When the planet shut down during the early COVID-19 pandemic, seismic noise dropped measurably worldwide. Scientists called it the Great Quieting. People literally heard the planet better because we were all standing still. The implications go beyond curiosity. The Earth is a system that vibrates, that rings, that hums. Every ocean wave, every earthquake, every footstep, every passing truck contributes to the symphony. We have become loud. The planet is louder because we are here. And at the same time, the planet's natural music is shifting because the oceans are shifting and the climate is shifting. In a sense, listening to Earth's hum is listening to the breathing of a living planet, a planet whose breath has been steady for billions of years, a planet whose breathing is now changing as everything that affects it changes. While the planet hums, scientists are racing to make sense of all these signals together, because individually, they are anomalies. Together, they may be telling a single story. Take a step back. Look at what we've covered. The inner core is reversing direction. The outer core is slowing. The magnetic field is weakening over the South Atlantic. Reverse flux patches are eating away at the shield. The North Magnetic Pole is racing towards Siberia. Days are getting shorter. The Chandler Wobble has collapsed. The polar axis is drifting east. The Atlantic conveyor belt is weakening. The Gulf Stream is showing signs of stress. Ice sheets are crumbling faster than predicted. Permafrost is thawing. Sea levels are accelerating. Auroras are appearing where they shouldn't. Fireballs are doubling in number. A strange interstellar object passed through with 22 anomalies. Solar flares may be triggering earthquakes. The ionosphere is more reactive than usual. The magnetic field has a second weak spot growing fast. The inner core may be soft and morphing. That's a lot of unusual things happening at the same time. This is confirmed. Every individual phenomenon is documented in peer-reviewed scientific literature. The natural question is whether these changes are all connected, or are they coincidences, unrelated events that happen to be unfolding in the same era? The answer depends on how you look at the data. Some changes are clearly connected. Ice melt redistributes mass and shifts the spin axis. Slowing core rotation accelerates surface rotation. Weakening magnetic field over the South Atlantic exposes satellites and astronauts to more radiation. These connections are well-established physics. Other connections are suspected but not proven. Could core changes be linked to climate changes? Some researchers have proposed that subtle shifts in deep Earth dynamics might affect ocean circulation and atmospheric patterns over long timescales. The evidence is suggestive but not conclusive. Could solar flares trigger earthquakes? The mechanism is plausible, but the statistical case is still being built. Then there are the anomalies that look unrelated but emerge in the same window. The interstellar object 3I, Atlas, arrived and started showing strange behavior at the same time the inner core was reversing, and the South Atlantic anomaly was splitting. There's no known physical connection, but the temporal coincidence is striking. What scientists agree on is this. Earth is currently in a phase of unusual change across multiple systems. The deep interior is shifting. The magnetic shield is weakening. The atmosphere is changing composition. The cryosphere is collapsing. The oceans are warming and circulating differently, and the entire planet is responding to a sun that has entered a particularly active phase of its cycle. Picture the planet as a vast orchestra. For most of recorded history, the instruments played in familiar harmony. Now several sections are playing different melodies. The string section, the magnetic field, has gone slightly out of tune. The percussion section, the seismic activity, is more intense in some places. The wind section, the atmosphere, is louder than before. The choir, the ocean currents, is shifting tempo. The whole symphony is more chaotic, more unpredictable. For some scientists, this is alarming. The simultaneous changes suggest that Earth's various subsystems are more interconnected than we realized, and that pushing one too hard can cascade into all the others. For others, this is a normal phase of planetary evolution that we happen to be witnessing because of our improved instruments. The truth probably contains elements of both. What is undeniable is that we are living through an unusual moment in the history of our planet. A moment when many things are changing at once. A moment when scientific instruments capable of measuring those changes finally exist. A moment when humanity has become a planetary force in its own right, shaping the climate, the rotation, the surface, and the magnetic environment of the world. The next chapters look at where this all might be headed, because the changes we're tracking are not the end of the story. Far above your head, the atmosphere fades into space. There's no sharp line. The air just gets thinner and thinner until there's almost nothing left. The boundary, often placed at the Kármán line about 100 kilometers up, is somewhat arbitrary. The point is that the atmosphere has a top, and what happens at that top matters more than most people realize. The upper atmosphere is shrinking. According to research from NASA and other space agencies, the layers above about 50 miles in altitude have been steadily contracting for decades. This is confirmed, documented by satellite drag measurements going back to the 1960s. The cause is, paradoxically, climate change. While the lower atmosphere warms because of increased greenhouse gases, the upper atmosphere actually cools. Carbon dioxide, the same gas that traps heat near the surface, radiates heat away at high altitudes. As more carbon dioxide accumulates, the upper atmosphere loses energy more efficiently. Cooling causes contraction. The upper atmosphere is shrinking because it's getting colder. To picture the effect, think of a balloon. Heat it and it expands. Cool it and it contracts. The thermosphere, the layer where most low Earth orbit satellites fly, is doing the latter. It's slowly pulling closer to the planet. What does this mean? In the short term, less drag on satellites. With a thinner upper atmosphere, satellites can stay in orbit longer without needing to boost themselves back up. That sounds like good news, but in the long term, it's a problem. Less natural cleanup means more space junk accumulates in low Earth orbit. Defunct satellites, rocket stages, and debris from collisions stay aloft for decades or centuries longer than they would in a denser atmosphere. Space junk is already a growing crisis. In recent years, multiple satellites have had to perform emergency maneuvers to avoid collisions with debris. The International Space Station has had to dodge fragments multiple times. Each collision generates more fragments, which can collide with more satellites in a runaway cascade scientists call the Kessler syndrome. A shrinking upper atmosphere accelerates that cascade by reducing the natural cleanup that gradually pulls debris back to burn up. There's another effect. As the upper atmosphere contracts, the boundary between the atmosphere and space drops slightly. Satellites that used to fly safely above the atmosphere may find themselves operating in regions where rare atmospheric particles still exist. Spacecraft, designed for the conditions of 2 decades ago, may face slightly different conditions today. The shrinking atmosphere also affects how the ionosphere behaves. Lower density means different electrical properties. Communications, GPS, and navigation can be affected. The same trend that makes space junk linger also subtly modifies the conditions for radio signals and satellite operations. What about the lowest layers of the atmosphere, the ones we breathe? Those are expanding slightly because they're warming. Surface and lower troposphere are getting warmer. The upper layers are getting cooler. The atmosphere is being squeezed from above and stretched from below. The whole vertical structure is being reshaped by the same forces that are driving climate change at the surface. Future generations of children may grow up in an atmosphere thinner at the top, thicker at the bottom, with different patterns of weather, radio propagation, and satellite behavior than their grandparents knew. The sky itself, the very air around our planet, is changing in measurable ways. And the changes don't stop with the atmosphere. They reach all the way to life on Earth. Scientists have studied animal navigation for decades. The findings are remarkable. Sea turtles, salmon, songbirds, monarch butterflies, and many other species use Earth's magnetic field as a kind of internal GPS. They sense the field, they navigate by it, they migrate thousands of miles using the magnetic information that surrounds them. This is confirmed, documented in laboratory experiments and field studies across many species. How animals sense the magnetic field is still being unraveled. In some birds, specialized cells in the eye contain a protein called cryptochrome that may respond to magnetic fields through quantum mechanical effects. In sea turtles, Magnetic crystals in the brain appear to act as tiny compasses. In bacteria, chains of magnetite minerals align with the field and physically rotate the cell. Different species evolved different ways of detecting the same fundamental signal. The signal is so important to life that nature has come up with multiple solutions for sensing it. Now consider what happens when the magnetic field becomes more chaotic. Reverse flux patches over the South Atlantic, the magnetic North Pole racing towards Siberia, geomagnetic storms producing auroras at low latitudes. The field that animals have relied on for tens of millions of years is shifting in ways unprecedented in the history of any living species. Sea turtles return to the beach, where they were born to lay their own eggs. They imprint on the magnetic signature of that beach as hatchlings. Decades later, they navigate back to the same spot using that imprinted memory. But the magnetic signature of any given beach changes over time as Earth's field shifts. Recent studies have shown that beach signatures along certain coastlines have moved significantly. Some turtle populations now arrive at slightly different beaches than their genetic instincts originally targeted. Salmon have a similar story. They imprint on the magnetic field of the river where they hatch, then return after years at sea to spawn in the same river. Climate change and magnetic shifts together may be disrupting these ancient navigation systems. Salmon populations have been declining in many regions, with multiple causes contributing. Birds may be even more affected. Migratory species cross continents using magnetic cues, star patterns, and visual landmarks together. As Earth's field shifts, birds may need to recalibrate their internal maps. Some studies have documented changes in migration routes and timing that correlate with magnetic field changes. Other species are arriving at breeding grounds out of sync with the food sources they depend on. The mismatch can lead to population crashes. Monarch butterflies make one of the most extraordinary migrations on Earth, traveling from Canada to Mexico over multiple generations. They use a combination of solar position and magnetic cues to navigate. Monarch populations have crashed by over 80% in recent decades. Multiple causes contribute, but disruptions to navigation may be one of them. Picture an ecosystem as a vast, interconnected web. Each species has its role. Each role depends on countless cues from the environment. Magnetic navigation, sunlight patterns, temperature gradients, the timing of seasonal changes. If any of these cues shifts faster than species can evolve to respond, the species suffers. Some adapt, some die out. Most lose individuals along the way. The changes happening in Earth's magnetic field, climate, and rotation are happening fast on biological timescales. Species that took millions of years to evolve, their navigation systems are being asked to recalibrate within decades. Some will succeed, many will not. The wave of magnetic anomalies, climate changes, and ocean shifts could be contributing to the broader extinction crisis already underway. Earth's anomalies aren't just abstract scientific curiosities. They reach down to the lives of every creature that calls this planet home, including us. For most of human history, the space around our planet was a mystery beyond reach. Then satellites changed everything. We could finally see how Earth fits into the larger cosmic environment. And what we found over the past decade has been increasingly strange. The solar wind, the constant stream of charged particles flowing from the sun, has been measured in detail by missions like Parker Solar Probe and ESA's Solar Orbiter. These spacecraft have revealed that the solar wind is more turbulent, more variable, and more unpredictable than older models suggested. Magnetic field reversals within the wind itself happen more frequently than expected. The boundaries between fast and slow streams are sharper and more dynamic. This is confirmed, documented by recent solar mission data. Earth's magnetosphere, the region of space dominated by our planet's magnetic field, responds dynamically to changes in the solar wind. As the wind has gotten more turbulent, the magnetosphere has gotten more turbulent too. Major reconnection events, where solar magnetic field lines merge with Earth's, have become more frequent during high solar activity. Each reconnection event allows charged particles to pour into our atmosphere, driving auroras and disturbing satellites. Beyond the magnetosphere, the heliosphere itself, the bubble of solar influence that surrounds the entire solar system, has been changing. Voyager 1 and Voyager 2 crossed the heliopause, the outer boundary of the heliosphere, in 2012 and 2018 respectively. Their data showed the boundary is more complex and asymmetric than expected. The heliosphere has been contracting in recent decades because of changes in solar activity and changes in the local interstellar medium. What does this mean for Earth? A weaker, smaller heliosphere means less protection from cosmic rays from outside the solar system. Cosmic rays are extremely high-energy particles, often from distant supernovae or other violent events. The heliosphere normally deflects most of them. As the heliosphere shrinks, more cosmic rays reach Earth. Combined with a weaker geomagnetic field over regions like the South Atlantic, the radiation environment near Earth has subtly changed. Aircraft at high altitudes, especially polar routes, receive higher cumulative doses than they did decades ago. Astronauts face elevated cancer risks. There's another factor. Our solar system is moving through different parts of the galaxy. Over millions of years, the Sun has carried Earth through dust clouds, interstellar gas streams, and regions of varying density. Some researchers have proposed that we may be entering a region of higher density, which could compress the heliosphere further. The evidence is preliminary and disputed, but the possibility that Earth's cosmic environment is changing because of where the Sun is in its orbit through the galaxy is intriguing. Then there are the interstellar visitors. 3 confirmed objects from outside our solar system have been detected since 2017. Before 2017, no such object had ever been observed. 3 in less than a decade is a remarkable rate. Either interstellar objects are far more common than we thought, or our detection capabilities have suddenly improved, or both. Some scientists wonder if more such objects will be detected in coming years as observation networks improve. Picture our planet as a small ship sailing through an ocean we are only beginning to chart. For most of history, we couldn't even see the waves. Now we can, and the ocean is more dynamic than we expected. Currents shift, storms appear and disappear, strange objects drift past. The waters around our planetary home are not the calm, predictable medium that older science fiction imagined. The cosmos is closer to us than ever before. Closer because we can finally measure it. Closer because the boundary protecting us is weaker than it used to be. And the question that haunts every scientist studying these changes is one that no one wants to ask out loud. Stand back from the data one final time. All the threads we followed, the reversing core, the torn shield, the wandering pole, the collapsing wobble, the shortening days, the thawing permafrost, the crumbling ice, the slowing conveyor, the strange visitor, the roaring fireballs, the shifting auroras. Then ask the question, what does it all mean? This is theory. The interpretation of all these changes together is not settled science. Each individual change is documented. The big picture is debated. One interpretation is calm. Earth has always been a dynamic planet. Its core has always shifted. Its magnetic field has always wandered. Its climate has always changed. We are simply living in an era when our instruments are finally good enough to see all the changes that have always been happening. The anomalies are not new. Our perception of them is new. From this view, there's nothing to fear. Earth is doing what Earth has always done. We're just watching more carefully. Another interpretation is alarmed. The simultaneous changes across so many systems suggest cascade effects. Push one part of the climate, and the rest of the climate responds. Disturb one part of the magnetic field, and the rest of the field rearranges. The interconnected nature of Earth's systems means that pushing too hard in one place can ripple through everything else. From this view, the anomalies are warnings, subtle nudges from a planet under stress. The most likely truth combines both views. Earth is a dynamic planet. Earth has always changed. But we are now adding human-scale forces to natural processes. We pump water from aquifers that took 10,000 years to fill. We melt ice sheets that have lasted millions of years. We change the composition of the atmosphere in centuries when natural processes work over millennia. The combined effect is that Earth is changing faster than at any comparable period in its recent history. And our infrastructure, our cities, our agriculture, and our culture were all built for the more stable conditions of the past. What can humanity do about it? More than nothing, less than everything. We can monitor better satellites, better seismometers, better climate models, better space weather forecasts. Knowing what's happening is the first step toward responding wisely. We can adapt, build seawalls, reroute migrations, strengthen power grids against geomagnetic storms, move infrastructure away from sinking lands, develop crops that tolerate new climates. None of this is easy. None of it is cheap. All of it is necessary. We can mitigate, reduce greenhouse gas emissions, limit groundwater depletion, protect ecosystems that buffer us against change, slow the human contributions to ongoing trends so that natural cycles dominate again. We can study. The deeper we understand Earth's systems, the better we can predict what comes next. Every dollar invested in basic Earth science returns something invaluable, knowledge of the planet that supports us, and we can prepare for the magnetic shield to weaken further, for the fireball numbers to keep rising, for the conveyor belt to slow, for more record short days, for auroras in more strange places, for a planet that is, in many respects, becoming a different version of the planet we grew up on. Earth is a living world. The signs we've explored in this script are not the heralds of doom. They are the heartbeat of a planet in transition, a heartbeat that has always existed but is now louder than before. A planet that is reminding us, in many small ways, that we live on a dynamic stage, surrounded by forces older than humanity and stranger than fiction. The next decades will bring more anomalies, more records broken, more changes that surprise and unsettle. But humans have always lived on a changing planet. Our ancestors survived ice ages, supervolcanoes, magnetic reversals, and asteroid impacts. We are descendants of survivors. We have the tools, the knowledge, and the curiosity to face what comes. What we choose to do with all of this is up to us. The story of Earth is still being written, and right now, you and everyone alive at this moment have a front row seat to one of the most remarkable chapters in our planet's history.